We'll now yeah. Can you see the slides?
Yes, sir.
Yeah. So in the last class, we uh, uh, what we did is microcanonical ensemble, and in the last few classes we have been doing ensemble. So I hope the notion of ensemble is clear to all of you. So basically, you can see this is a brilliant construct. This ensemble, this notion of ensemble is fantastic. Once you have ensemble notion, then this notion, then you can think of a distribution function in that particular ensemble. And if you know that distribution function, actually it gives you a prescription to calculate the distribution function, then actually you can calculate averages. So the equilibrium properties you can calculate using the notion of ensemble. This is fantastic. Okay, so we have done microcanonical ensemble, which basically means that our system has some fixed number of particles and the volume is fixed V, and the total energy of the system is fixed E. Okay, but there are many other ways you can construct on ensemble. Okay, so one very popular, few popular ensembles are listed here. One very popular ensemble is called canonical ensemble, which is more practical because in experiment you can keep temperature constant. So in this case, the temperature is kept constant and the number of particles and the total volume of the system is kept constant. So today we'll talk about this canonical ensemble. Okay. But before we move to canonical ensemble, a short revisit to microcanonical. So microcanonical ensemble, each member of this ensemble, which is a collection of systems, they have the same number of particles, volume, and energy fixed. So they are like isolated system. Is this clear that they are isolated system because the energy is not changing?
Yes, sir.
I take one of the systems NVE, then you see that the same energy can be. So if I fix my energies as equal to 8, and if I take 4 particles which are say in this case indistinguishable, and you have 4 energy levels available shown here 0, 1, 2, 3. Then you see that at least there are 4 ways you can put these particles in these energy levels and you get the same energy. So these 4 arrangements we'd call 4 different microstates. So different microstates can give rise to same macrostate. Okay, this is clear though. This must be clear. Okay.
Yes, sir.
Yeah. So now we move to what is known as canonical ensemble. Okay. Now canonical ensemble means, what is canonical ensemble? So canonical ensemble is constructed as follows. First of all, this ensemble is something where the number of particles, total volume, and temperature, these are kept constant. Okay, and how do you can mentally construct or you can actually think of this ensemble? So what you can do, you can take, say, many systems. Okay, many systems, and they have different energies, same number of particles and volume, but different energies, E1, E2, E3, E4, like this, and you put them next to each other. So what will happen? They can exchange energy because they are made in such a way that they can exchange energy. The walls are such that heat exchange is allowed. So these energies will fluctuate. So the energy exchange is allowed between these systems. They have the same number of particles and volume. The volume cannot change. Number of particles cannot change because particle exchange is not allowed. And then the whole, then you have huge number of such systems, and the whole system, the super system I call it, is actually coupled to a temperature bath or heat bath at temperature T. And if you couple it, so if you couple it, the whole system, if you couple it to a temperature bath T, and if you wait sufficiently long, what is going to happen? That the whole system will attain a temperature T. So each member of this system, like these tiny systems, this would have same temperature T. So rather than writing it NVE1, NVE2, NVE3, I can write them as NVT, 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 NVT. Okay. So is it clear? So we have a thermal contact between the individual systems, and the systems are kept at temperature T, where the super system, the collective system, is kept in a bath of temperature T. Is this clear?
Yes, sir.
Yes, sir.
This statement should be clear. No. Now, see, temperature fixed does not mean energy is fixed. They can exchange energy between each other, isn't it? For example, say I give you a value of E1. E1 is 6. If E1 is 6 and I have say 4 particles and these are the energy levels available, I can see at least there are 5 ways I can arrange these particles, isn't it? So with a fixed value of energy, I can have 5 microstates, like canonical, microcanonical ensemble. But then I change the energy. I change this in E1 value to 8. Then I can have different arrangements. So I can change this E1 value to 10. Then I can have different arrangements. Okay. So basically, here these energies can change. So as a result, for a given energy, I can have many microstates. But as the energy changes, I can have even more number of microstates, because energy is also allowed to change here in this construct. Is this clear?
Yes,
Yes,
sir.
sir.
Yeah, this is not very difficult. Just now, what I do here, say, what I do here is that, okay, I say that there are ns total number of systems. Okay, this total number of systems. Okay, and I can have something like n number of particles in each system. Okay, is this clear? So n number of particles in each system, and ns is the total number of systems. So I go back to this picture. So I have like 1, 2, 3, 4, 5, 6, like ns number of systems, and each is having n particle. Okay, so the super system, how many particles are there?
ns into n.
Yeah. So I can think the total number of particles this is total number of particles, isn't it? Or molecules, what do you want to call it? And similarly, I can have a volume, like each has a volume V. Okay, and how many are there? I can similarly have a total volume is something like ns times V, isn't it? Total volume.
Yes, sir.
Yes, sir.
Okay, and then I can keep on adding these energies, E1, E2, E3, E4, E7, isn't it? See, the super system is in contact with temperature bath T. The super system is isolated. You understand? This small system, they can exchange energy, but the super system cannot, because it is coupled with temperature bath, and the whole thing is isolated from the universe. So the super system energy has to be conserved. Is this clear?
Yes, sir.
So basically, this is total energy. So this must be. Can you tell me what is this going to be?
Sum over I.
So ideally, if I say, it should be something like E1 plus E2, like this, no? If you think.
Yes, sir.
But actually, you see that there are if I go back to this picture, it is not that only one system has energy E1. I can have like 7 systems which are having the same energy E1, isn't it? I can cluster them into groups. You understand what I'm saying?
Yes, sir.
So rather than writing this, I'll do what?
Multiply by the
Some
degeneracy.
number. Yes. So we'll do that later. So basically, this is total energy. So this is like NT, VT, ET. This is isolated system, no? The super system. What is this? So then construct a microcanonical ensemble with this. You understand my point?
Yes, sir.
And there I can use the fact so there are 2 tier. The first tier is this, where you actually take systems with different energies, put them side by side so that they can exchange energy. But the super system is coupled to a temperature bar, so the temperature is fixed. For each system, temperature is fixed. And then I'll have the whole system will have a total number of particles, NT, volume VT, and total energy ET. So then I can construct another ensemble top of it. You understand? So this will be something like another microcanonical ensemble. You understand? Are you following? It is not very
Yes, sir.
difficult. Yeah, this should be clear. Okay, this should be clear. Okay, so with this, let us start doing this. I can do, of course. Then I have 2 constraints here. One is if I do this, this is equal to ns. You understand this, no? The total number of systems, I just divide the system into small cluster. That okay, there are n1 number of system with energy E1, n2 number of system with energy E2, like this. Okay, I go back
Yes,
to
sir.
this picture. Yes, like this. Here I am showing only E1, but there will be many such thing where you have NVE1, NVE1. No, I have not shown that. So here I assume that everyone, each one is occurring only one time. It is not the case. No, it can occur many times. So in general, I'll have this, and of course the ET. I can tell you that okay, what is going to happen if I take a sum of J times Nj. I think the notation is Ej. That should be equal to Et. Is this clear?
Yes, sir.
Yeah, you can read. I hope you can read. Okay. If you have any problem, just please tell me. Okay. What is that? Yeah. So these are, again, I have this information I have. These are constant actually. Isn't it? It will use
Yes,
this.
sir.
These are very important. These are constants. Now, in this picture, I assume that particles are indistinguishable. But if the particles are distinguishable, then I can always write that the number of ways you can arrange, that is actually the number of microstates, function of nj, because you have ns number of system and you divide this into n1, n2, n3, isn't it? Okay, so we'll elaborate this later. I am sure it is done in 408, but this is when the particles are distinguishable, you can do this. Okay, and then I can always ask, okay, what is the probability? Now, probability of what? I can think of probability of having actually observing a given state nj with energy ej. Yeah, so if I ask you this question, that what is the probability of observing a given state nj with energy ej, what will be the answer? What should I write? Any suggestion?
Sir, Nj here is the total number of states having the energy EJ, right?
Yes, nj is like yeah, like yes, like that. So this is a small cluster.
We can say Nj by Ns.
It is not nj by ns. That is the whole thing. Now, if I give you, for example, so nj by ns, it give you the fraction of I'd call it the fraction of members of that canonical ensemble in the jth energy state, isn't it?
Yes, sir.
But then you have to do another averaging, isn't it? Think about it. You have to do another averaging over this.
Sir, I guess multinomial distribution.
Yeah, but that is there, omega. So so what I'm saying, that is omega should come into the picture, isn't it? Omega should come into the picture, because see, these nj's are changing. No, I can I can do n1, n2, n3, then I can do something else. Okay, these are changing. Okay, you understand what I'm saying? I can have different nj's. I can have different nj's, because I can, in one case I make it n1, n2, n3. In another case I do make it n1 prime, n2 prime, n3 prime. But with the constraint that if I sum them, that is equal to ns. So many ways I can do. So this probability is very important that you do. How do we do it?
By Boltzmann distribution, if you think that this is
Well,
something.
I don't know what is Boltzmann distribution. So don't bring something which you know. We'll see what is Boltzmann distribution later, but
Sir, omega multiplied by a fraction of probability for each state.
you're almost there.
Is it Nj by omega?
It has to be Nj by Ns, somebody has said. But this Nj is not real Nj. You have to take an average of Nj with respect to this omega. So your Pj, right side, your Pj is going to be something like what I call Nj average by Ns. Think about it. Why? Because I give you n number of particles, ns number of, you have ns number of system, no? And you put like, you understand, no? You have ns number of system, and you divide that into n1 number of system, into number of systems. But this is not unique, no? Many combinations can give me this with the constraint that n1 plus n2 plus n3 equal to ns.
Yes, sir.
So for example, so in order to calculate the probability, overall probability, the system is the jth quantum state. You have to average this over all the allowed distributions. Allowed distribution means all the possible arrangement of these Nj's. If it is not clear, you go back and think about it and come back. We'll discuss it again in the next class. But this is not Nj by Ns. Nj by Ns give you only a fraction, of course. But then you have to take an average of this Nj over all possible distribution. And these all possible distribution will be given equal importance. So if I write down it very explicitly, this one is going to be what? 1 over Ns sum over J. I think, yeah, yes. Sorry. Is this clear? So can you do you understand this part, the second part? This part you
No,
understand? This part you understand, no? This is nothing but your some kind of average of your Nj. You take the average of Nj over what? What is the distribution function? Is omega. What is omega? Omega is this, given by this. How many ways you can arrange? Okay, so let me proceed. I think it will be clearer if you have to think, and maybe we'll come back in the next class. So let us proceed. Okay, so we'll proceed with these two equations.
This omega is something related to the possible microstate for a given state of given system J.
Yes. It is the number of ways that it can be. It's number of ways you can distribute.
Okay.
I am not writing the full statement. Okay.
So,
if you have ns number of, say, entities, and you group them into n1, n2, n3, then how many ways you can do it? That is omega.
so if you think about the factor in the numerator, so this will be something related to the all possible distribution.
Yes. So this is nothing but this is like Pj times Nj divided by sum over Pj, isn't it? So omega is like that. Okay. Omega is like that. It's clear. So let us do this, because you have see, and then this is your Pj. But what we'll do, that we'll approximate this with something else. we will say it is 1 over ns. This is like a sum, no? Each sum will contribute. Now coming back to this, that okay, it is going back to your previous day, going back to our previous day's lecture. You see that you remember that the omega for the combined system had a peak. Remember that? Somebody had
Yes,
asked
sir.
whether it is violating equal a priori postulate. I said no.
Yes, sir.
So, like here, this sum will have different terms, but we'll take only one term. What is that term? That is the most probable term. So it's the most probable nj star omega nj, you can call it nj star, divided by omega nj star, and what will get? And this is going to be equal to nj star by ns. Okay, nj star by ns. So the question is as follows: what is the probability of observing a given state nj with energy ej? Here energy is ej and the given state is nj. Okay, but that is equal to nj star divided by total number of systems, ns. Make this thing very clear. It is not nj divided by ns. It is nj star divided by ns. You have to take an, actually it is nj average divided by ns, but then you approximate this nj average by its most probable value. Okay, this is the most probable value I am taking because it has peak, and I am just taking that. So I suggest that you read these two books. The book by Biman Bakshi for this, and there's a book by Mercury. So you just read both these two books and come back if you have any problem. They have a chapter on ensemble. If you read these two books, it will be clearer. Okay. How many of you have access to these books? I think many of you
Yes,
have, no? Many of you had, no?
Yes,
Yes,
sir.
sir.
Yes, sir.
So basically, I take a value of nj that maximizes this distribution, isn't it?
So if I want to get something clarified. Nj is so omega of bracket nj is basically the frequency of having that particular value of that number of elements in the cluster, and nj star is the one having maximum frequency. Is it?
Yeah, of course, of course. nj star has the maximum frequency, of course. Of course. Okay. And you should not confuse this with equal a priori, because equal a priori is for a given E. If I give you value of E, for that given E, all the microstates are equally probable. But if I give you different values of E, no, not that everybody will have equal number of microstates and not all are equally probable. You understand what I'm saying? That is exactly what I did in the last class. For a given E, all the microstates are equally probable. But if I change E, your microstates will change. So like I go back here, this picture. For this E, I have like 6 microstates, no, 5 microstates. Huh? All are equally probable. Now I change E from 6 to 8. How many are possible? 4. All are equally probable. But I cannot compare these two, whether this one is more probable, this one more probable. I should not do that. I should do it only when energy is fixed, E is given. Then only I should up. So equal a priori will give you equal probability for all these states, equal probability of all these states, equal probability of all these states for a given E. Okay. So nj star is the value of nj which maximizes your omega. Okay. which maximizes the omega. And how do you maximize this omega? That I'm going to do in the next slide. What you do, the usual thing is this omega is a huge number, so it's exponential in n, okay, number of systems. So you take a log of this omega. And maximizing means what? You have to take a derivative of this with respect to nj, and then you should put it equal to what? Tell me. You should put it equal to 0, but there is a constant. What are the constant? One constant is this.
Total energy and total number of systems.
Yes. You have this to constant, and what
Yes,
you do,
sir.
you put to constant there. These are called, these are called undetermined.
multiplier.
You know that. Okay. So, and then the whole thing has to be equal to 0. Is this clear? Now, let me do one thing. If I have a very large number n, ln n factorial is given by ln n minus n. And this is the name. What is this called?
Stirling approximation.
Stirling approximation.
This is called Stirling approximation. Okay. So your ln omega, I am just writing omega here, or I can write whatever. This is going to be what? Equal to ln ns factorial minus ln what? Like this. Can I write like this?
Yes, sir.
You understand, no? Because you had like n1 factorial into n2 factorial. This one I can write it as some nj factorial, isn't it? This is exactly
Yes.
I did. So what will happen to this? This is going to be ns ln ns. If I use Stirling minus ns. What will happen to the next term? Tell me what is going to happen to the next term.
Product nj.
So this is
Log.
actually, you just think, this is like n1 factorial times n2 factorial, log, you take log of that, isn't it? So basically, isn't it? So basically, this is, if I can write it as nothing but sum over j
Log nj
ln
factorial.
of nj factorial, isn't it? This is,
Yes.
this is a logarithm. So let me write down here. It's going to be ns ln ns minus ns, and this one becomes within the sum nj ln nj minus nj. Fine.
Yes, sir.
And what is this sum over nj? This is ns. Remember, no? Because you have these two constraints, no?
Yes, sir.
And I have this constant also. So this ns will cancel, because this will be plus actually. This will cancel, huh? Isn't it? It will cancel. Is this fine?
Yes, sir.
It should not be a problem, no? Because nj ln nj sum plus sum over of nj. Sum over of nj is ns. It is coming with plus. So plus and minus cancel. So what I have here is ns ln ns. Okay, and this is your ln omega. Is this clear? So if I do d, the first term, this first part, if I take a derivative of that with respect to nj, what is going to happen? First term will give you 0 because this is ns, isn't it? The second term will give me what? Sum over j. There will be two terms, no? Nj divided by nj, because you take log, minus is it clear? Is this clear?
Yes, sir.
But I have done something wrong. What is the wrong thing here?
There shouldn't be a summation, right?
Yes, because you are differentiating respect to particular j, nj, isn't it? So there should not be a summation. What you get is this. These two terms, huh? This is fine?
Yes, sir.
What about the next term? Alpha. This time is going to be alpha. Is it all? And the next term is going to be minus beta ej,
EJ.
and the whole thing has to be equal to 0. So basically what I have here is this will give me 1. So what I have here is minus 1 minus ln nj, and this nj is something which maximizes my omega, so it is nj star. And also I can put this, okay, this is nj star, so this is equal to minus alpha minus beta ij. Any problem you can tell me. What is the next term? Next step will be I take ln nj star on the other side. If I take on the other side, ln nj star is something like 1 plus alpha. I hope I have not done anything wrong with the sign. Is this clear? Is this fine? Let's just have a look. This is nj, no? You understand? It is not written properly. This is fine?
Yes, sir.
So I can call it alpha prime. This one is alpha prime. This is beta ij. Here alpha prime is 1 plus alpha. So if I take exponential on the both sides, what I'm going to get, nj star equals to is this fine?
Yes, sir.
Yeah, it is not a very difficult thing to do. Okay. Now what should I do now? How do I calculate alpha? Any suggestion? So again I go back to this constraint that, okay, if nj, sum of nj is ns, then sum of nj star is also going to be ns. Okay. And if it is ns, then what is going to happen? This is going to be e to the power of minus alpha prime ej, or alpha prime is equal to it is alpha prime is equal to plus alpha prime if I write like this. So this will lead to my pj, which is pj or pj star, what you want to call it, which is your nj star by ns. This is going to be what? Ns divided by into this is your this into to the power of minus beta epsilon j, of course. So what is the answer? Does it look familiar to you, some of you?
Boltzmann distribution, I guess.
Does it look familiar? It should look familiar to some of you at least.
Yes, sir.
Something Boltzmann distribution.
Yeah, actually we are getting what is known as Boltzmann distribution. Okay. And this quantity I'm calling it Q. The function of n, of course, P and T. And this is a name. What is this called? This is
Partition
called
Partition.
canonical partition function. Because omega was microcanonical partition function, no? It's called canonical. It's clear? And this is known as Boltzmann distribution. It actually tells you only about, if I give you energy Ej, then what is the probability of having the state with energy Ej? Okay, this is given by Boltzmann distribution. What about beta?
1 upon kb.
We'll see later. And we'll show that beta is 1 over kVt. That will show later. Okay. Now let us calculate few quantities. Beta will take later. Let us calculate few quantities. Let us. Okay, we can just calculate beta first. First of all, we can calculate beta. So, in order to calculate beta, E average, what will be the answer? You know this. This is fine if I write like this. This has to be a sum of Pj, isn't it? What is this? This is Ej. You know Pj is exponential of minus beta Ej. Fine? You're fine with it? And if I take dE bar, d actually essentially, what is this? Is this clear?
Yes, sir.
This is just, you know, that because the exact differential and you know what to do. Now, what does Pj? Pj was, sorry. Pj was exponential of minus beta Ej divided by Q, isn't it? Q is this one. So if I take log of ln of Pj, what is the answer? Minus okay. This is fine?
Yes, sir.
Yes, sir.
Or I can actually write that your Ej, if I take Ej, Ej is minus 1 over beta times ln Pj plus ln q. Is this clear? This is your EJ.
Yes, sir.
And I take this EJ and put it here. What I get? I get EJ is minus 1 over beta Pj, and this one I can write it like this. Depends on volume, so I can write it like this. So essentially I have these two terms in your DE, D average. D average, you have these two terms. Is this clear?
Yes, sir.
Can I further simplify this? Yes, I can. It is the first term as 1 over minus beta outside j ln pj into dpj, isn't it? This is the first term you have. Okay. What is the second term? Second term will also have minus 1 over beta ln q also come outside rather, and sum over dpj. But what is sum over dpj?
1.
This is 0. This is 0. Sum over pj is 1, so sum over dpj is 0. Plus pj okay. Any problem, you tell me. So what I have here is minus 1 over beta ln pj dpj plus I have simplified expression for d. So this E bar is nothing but your internal energy, thermodynamic internal energy, isn't it? Average of E is thermodynamic internal energy,
Yes,
isn't
sir.
it? Now again I go back to this definition of entropy. S is minus Kb ln Pj. You remember this, no? This gives definition of entropy. I hope you remember.
Yes, sir.
Now if this is so, then what is your ds? ds is going to be Kb d of this. What will be the expression? Tell me. Tell me. I will have first term will be like Pj by Pj into dpj plus
Sum over j log pj dpj.
it's fine. Again, what will happen to this term?
0.
0. So what I have here? Is this clear?
Yes, sir.
So I have ds, I have d. Okay. So now d also I can write a slightly different way. I know that ds is this, and d has two terms. These two terms look very similar, isn't it?
Yes, sir.
They look very similar. So I can write, combining these two, I can write that dE is equal to minus 1 over beta into minus, so yes, I can write, okay, so ds is this. So essentially what I can write, that I can
Minus
replace the whole thing by minus ds by kb.
maybe.
Okay, plus so essentially what I have here, minus will be plus, so I'll have 1 by beta kb into ds plus pj this is fine. I hope this is fine.
Yes, sir.
Okay, this is like this is like this. Okay, now I know from thermodynamics, what I know is as follows, that okay, that my dE is equal to this is pressure, huh? And if I compare, so this equation is A, this equation is B. What will give you if I compare A and B? This will tell you
T is
that your
equals to
T
1 over
equals
beta
to,
kb.
which basically means beta is
1 over kbt.
so fine. I hope you're fine with this.
Yes, sir.
But that is not the whole story. It also tells you, let me write down here, that if I compare this with this, so your pressure is minus. It also gives you prescription to calculate pressure starting with Boltzmann distribution. This is Boltzmann distribution. This is pressure, huh? So I have these two. One is this, other one is this. Comparing A and B. Okay.
Yes, sir.
So now I go back to the next stage. What should I do? So let us now calculate E average. Now before we calculate E average, I have this canonical partition function Q. This is given by J, where okay, let us keep it beta. It will be easier. I'll write kbt later. If I take a log of this, you know what is going to happen. Log of Q is what? But you cannot take log of sum, no? Sum of quantities, no? It is not log of A plus B is not log A plus log B. You know that. Huh?
Yes, sir.
Don't make that mistake. You can write only up to this. Now, if I take a derivative of this with respect to beta, what I'm going to get? Tell me. I am going to get what? Can anyone tell me? First of all, this argument will come down because it's a log of some function of beta. Then I'll have minus Ej times
power minus beta is
Is this clear? Is this
somehow
clear?
it's numerator, isn't it?
No. Why? Why the sum in the numerator? Yes. Of course. Yeah, sum. This one you're saying, no? So what is this? This is equal to what? This is minus
Average of energy.
yeah, and this is minus of. Yeah, understand? No, this is not very difficult
Yes, sir.
because this is your average of energy, because this is nothing but sorry. Was it done in 408? Tell me.
Yes, sir.
It was done, no?
But notations are different like that.
And notation does not matter, but it was done, no?
Yes, sir.
So you know all this. That's good.
But I am not remembered, sir, actually.
Okay, that can happen. So this is how it is. Because your PJ, I just say this is. Okay. So in other words, also I know that now I know beta is equal to. So this will give you d beta equals to. Is this fine? So then it tells you that okay, your E average, which is minus d ln q d beta. What actually it is what? E average is actually, if I write in terms of temperature, it will be. Are you convinced? Of course, number of particles in the volume is constant. So actually now I can express your internal energy as a function of, not function, derivative of log of your partition function. What else I can do? So let us try to calculate average pressure. How would I calculate average pressure? How would I calculate average pressure? Again, I go back. I take a derivative of this with respect to volume. What will be the answer? Okay. And then I have to, this beta will come down, of course. But then it is little difficult. Different? Why? Because you have exponential of beta ej times del ej del v. Can I write like this?
Yes, sir.
And what is this again? Minus what is this? I go back to the previous slide. I should have it somewhere. This is nothing but this.
Pressure.
I hope I have not done anything wrong. I hope. So this is going to be beta times pressure. So in other words, pressure is 1 over beta is kBt, you know. This is another useful quantity I can calculate from the partition function. Okay. What else I can do? Let us try to do entropy. But before I do entropy, let me write down this S. What is S?
Minus kb sum over j pj log bj.
Yeah. So let us put this expression. I'm putting beta, later we put kBt. So this will give me minus kb. You can like this. You can take the q outside, but let me keep it inside. ln of this will give me what? Tell me. First term will give me minus beta ej minus ln q. Fine. This is fine.
Yes, sir.
So the first term, if I combine, what we're going to get is kb into beta if I take outside. And what is kb into beta? 1 over temperature,
Okay.
isn't it? And what is this quantity? This is your
Average energy.
So the beautiful thing is you can also express entropy in terms of your partition function, because if I write it explicitly, it is going to be kbt square by t, which is kbt it is so powerful. You can see, if I know the partition function, you can calculate entropy, you can calculate pressure, you can calculate internal energy. Can you do a few more things? Can you go beyond this? Can you go beyond this? Any suggestion?
We can calculate enthalpy.
But within this ensemble, what I can calculate?
Free energy.
Yeah, but what kind of energy?
Helmholtz.
Helmholtz free energy.
Yeah, let us see. How do you know Helmholtz free energy?
Because V and T have been held constant and they are the natural variables of.
Yeah, you are right. You are right. So let us do this. How do you do? What is the definition of Helmholtz free energy? A. E
Minus Ts.
minus Ts. This, so A is E, you know. And minus Ts is minus and these two terms will cancel each other. And this is the most important relation of in canonical ensemble between the partition function and a thermodynamic quantity like Helmholtz free energy. You knew this, no? I think many of you knew this. So this is a thermodynamic potential. This Helmholtz free energy is the thermodynamic potential in canonical ensemble.
Sir, I have come across this term thermodynamic potential, but what does it really signify?
And see, what does it signify? It is like this. In this case, see this thermodynamic potential in this case it is actually all, even entropy is called thermodynamic potential, Gibbs free energy is called thermodynamic potential, depending on which ensemble you are working. So actually, if you construct, if you know the partition function in that particular ensemble and log of that partition function, you can multiply that with some constant, something like temperature. It will give you a thermodynamic quantity. It's called the thermodynamic potential in that particular ensemble. So if I go to microcanonical ensemble, what is the thermodynamic potential?
Entropy.
Yes, because you know S is in microcanonical ensemble. Any idea in which ensemble your thermodynamic potential would be Gibbs free energy?
MPT, yes, it's called isothermal isobaric.
The isothermal isobaric ensemble, it will be Gibbs free energy. If I go to grand canonical ensemble, which is mu Vt, you know pressure times volume itself is actually what is known as thermodynamic potential. Okay, so we'll talk about the thermodynamic potential again. I think your question is why it is called potential, isn't it?
Yes, sir. Like, what is the special thing about entropy in microcanonical, Helmholtz free energy in canonical?
First of all, actually, for example, you will see that if there is something called potential of mean force. I have two particles in a fluid, and I calculate the effective interaction between the two particles in fluid, and that will be equal to the free energy, the Helmholtz free energy, if I work in that particular ensemble. So in that sense, it is called potential of mean force. It is again, for example, it is like that. So it is like that actually. If I take exponential of this potential, I'll get the partition function, isn't it?
Yes, sir.
So basically, it tells you that exponential of this potential will give me something like number of accessible microstates. Why it is called potential, I have to read and let you know why exactly this term potential. But you see the structure. It is always log of a function, which
Yes, sir.
okay, log of a partition function. So any log of a partition function is kind of is a thermodynamic potential, isn't it?
Yes, sir.
I think in that sense, because in other areas of physics, you know that because we'll talk about it later. I think I'll try to make it better, not today. I'll make it better, but it should be clear that any partition function you give, take a log of that. This will give me some thermodynamic function, isn't it?
Yes, sir.
Now you have to understand that your partition function depends exponentially on number of particles is exponential of n kind of thing. If you increase the number of particles, your partition function grows exponentially with the number of particles in the system. Okay.
Yes, sir.
So
is it something, sir? Hello, can I say something?
yes,
Is it some whatever that thermodynamic potential we see in the particular condition? Is it something used to justify the feasibility for a process?
feasibility.
Likewise, yeah, that A is in particular that condition A is used to define a process is a favorable or not. If
Yeah, that we'll see. That we'll see. Okay, but why the term potential? The word, I think. Why it's called potential? That I have to check. I know kind of, but I have to double check and tell you. Of course, if you are working in this ensemble NVT, then then the kind of free energy you look at is Helmholtz free energy, because changing Helmholtz free energy will decide whether the process is spontaneous or not. If you go to NPT ensemble, it is free energy is Gibbs free energy, isn't it? That is a different thing. Why the question is why it is called potential. Okay. It has an analogy with electricity. In that sense, it is potential. In electricity, log of something gives you potential, isn't it? Hello?
How exactly?
I'm thinking. If I have it is linear, why it is called potential? I have to check and let you know. Okay. Yeah,
Yes.
but I was telling something I forgot because people ask me questions. So yeah, I was telling that Q, the partition function, grows exponentially. If I take exponential of n, if I take log of that, it ensures that all this potential like A and entropy, they are proportional to n, and this has to be, no, because these are extensive properties. If I increase the size of the system, then it should also increase linearly, no, with the number of particles in the system.
Yes,
Is
sir.
this clear? Yes. So as a result, so Q has something like exponential of n kind of dependence, and as a result, log of Q will have linear in n. So it essentially tells you that your Helmholtz free energy is proportional to n number of particles. Same is true for entropy. Okay, same is true for entropy. So I think we'll stop here because I have 10 more minutes today. But the problem is we cannot start a new topic, but we'll do a new topic in the next class. Okay, and we'll stop here. And in the next class, we'll start with grand canonical ensemble. And once we are done, we'll again have a class on these fluctuations, which is very useful for this course. And I've already uploaded a set of assignment. Did you see that today?
Yes, sir.
Yeah, so you have to submit it by 12th of February, 11:59, just before midnight PM. Okay, is this clear? And you have to submit it in the assignment mode. What does it mean? It means that you have to solve this on a piece of paper, white paper, using blue or black ink, right? You scan it, make a PDF and upload. Okay, I think some of you have done it in some other course, like I took a course called 812, some of you took that course, or 425, some of you took that course. The same way you have to do it. Any queries or any question on that?
Sir, we'll submit it where?
In the Moodle.
Okay.
You go to the Moodle, there you'll see that the assignment is, you click there on the assignment one, and you'll see there's a place to submit. So you have
Yes,
to
sir.
write
Yes, sir.
everything in black or blue ink, write your roll number also,
Hmm.
scan it, make a single PDF and upload, and don't copy from each other. And these assignments will carry marks. There are 15 problems in the first set. and you have to submit it by 12th. So you have 2 weeks. Okay. And for today's class, you please read the book by Mercury and Biman Bakshi, that chapter, ensemble chapter. And we'll revisit this. If you have question, we'll revisit. No, don't worry. Okay. So with that, I think I'll stop today. Okay, with that, I'll stop today. And so let me